You have fallen into Event Horizon with John Michael Godier. John is joined today by Gabriella Contardo. Gabriella Contardo is currently a research fellow at ESA, the International School for Advanced Studies in Trieste, Italy. She completed her PhD in machine learning at Sorbonne University Paris and then joined the Center for Computational Astrophysics at the Flatiron Institute in New York, where she developed her research program at the interface between data science and astrophysics. She works on topics such as dimensionality reduction, anomaly detection, and topological data analysis in various applications of astrophysics and cosmology.
Gabriella Contardo, welcome to the program.
Thank you for having me.
Now, Doctor, you have a new paper out that is part of a larger push, basically, to look into technosignatures. NASA has been having technosignature workshops, and there's been a lot of talk about it, that we should perhaps look within SETI above and beyond the radio spectrum. And in this case, the infrared spectrum, right, with the new paper. Now, what types of stars were you looking at with this study?
So in this work, we focus specifically on FGK star in the main sequence. So basically stars that would be similar to our sun to some extent. And so in this work, just to clarify, we don't only look for Dyson Sphere, although hopefully Dyson Sphere would fall in that regime, but this would need to be confirmed.
It has to be difficult to differentiate this type of signal between a star that has a debris disk and a star that potentially could be harboring a Dyson swarm. How do you tell the difference? Where do we go from here in trying to determine if there's a technological nature or if it was a deceptive star? In other words, it might be younger than it appears and therefore still have a debris disk.
You're asking the hard question. Like basically, this is the end of the paper, and right now, so basically, the paper finds candidates that shows access in the mid-infrared, but this type of access, as you said, could come from so what is dubbed as extreme debris disk, or could come from planetary collision, and they look quite similar from the data point that we have right now, because basically we have WISE data, which is 4 if we're lucky, 2 if we're not so lucky in the infrared, and so it's hard to say anything with two points, two observation on a star. So yeah, first in our set of candidate, we would have to match, for instance, first check with, so you've talked about Suazo's work and with Jason Wright as well, if any of our candidates would actually match their Dyson Sphere models that they built. And so it can be that some of this excess actually don't have the right morphology, or they wouldn't match any kind of like Dyson swarm or Dyson Sphere level of completion. And if they do match, we still have to eliminate, right, as you said, the other explanation. So if we see features that might indicate that the star is very young, so for some of our candidates, that might be the case. We have like this H-alpha emission, so that might indicate youngness in a star. Well, if it's very young, then it's very unlikely that it's the Dyson Sphere around it, right? But after that, you need to have follow-up observation. And even with this follow-up observation, for me, it's not obvious how you do you would distinguish properly between the Dyson Sphere or planetary collision or debris disk or other natural processes. So I would be curious to talk with Jason about that, actually.
It'd be interesting to know what the odds of a planetary collision in a mature star system really are, because if you look at the solar system, not much chance right now. We're not going to go and accidentally hit, Venus here. So it would seem to me collisional models eventually become lesser likely as the star system ages. Now that, of course, changes with the dynamics of the star. When it goes red giant, and all kinds of things can happen. But just in a nice stable, which it has to be said, the sun is type G, which is one of the star types that you looked at, as opposed to the other study, which was looking at mostly red dwarfs. But it used a different method. What was different between your study and the other paper?
First, if I can go back just to the first part of your comment, I think that's also super interesting kind of work. If we scale this kind of search, we will see more of this like anomalies in the infrared. So we might find more of these events, which might be, I mean, it's slightly, I don't know if it's more likely that it's a planetary collision than a Dyson sphere. I don't know if I can say that, but probably. And as you said, I mean, it would be nice also to have number around like some kind of like occurrence rate in terms of planetary collision. But as you said, it also relates to the age of the system, and getting like reliable age for star, I learned, is very hard. And so it's kind of like tricky to if we see a planetary collision, it would kind of like be assumed that it means that it was early on in the system, in the planet, it was post-planetary formation, but like still early in the system because you have instability in the orbit. But still, I think it's quite interesting. And so for the second part of your question, so the main difference from our approach to other approaches, and so in general, what we do is that we bypass sort of the need for having good stellar modeling. So when we say we're looking for infrared excess, it's an excess compared to like what we would expect from a star, from that star, assuming like a regular behavior and given the stellar type and whatever. And so usually what people would do is to have like a nice stellar model, right? But it can be quite computationally heavy to predict what the star is supposed to look like in the infrared. So people would rely on approximation and this kind of thing. And so if you have approximation, then I mean, it's not so great either, right? So what we do is basically we use machine learning to bypass the need for stellar modeling and basically knowing the astronomy and the astrophysics. And so then we can say how this machine learning model tells me what this star is supposed to look like based on other information that we have on that star, which is basically observation at other wavelengths. And if the observation disagrees strongly with the machine learning prediction, plus a bunch of like check on like if we have consistent disagreement and like quality check on the observation and so on and so forth, then we deem this as an infrared excess. And so that's how we do the detection. And additionally, we work compared to other works, instead of working in the what we call W3 and W4 band in WISE, which is like more in the infrared, we work slightly closer to the mid or the near infrared with W1 and W2. And that allows us to like unlock a lot of data, because W3 and W4, you need to be quite careful, and like when you do this search, you need to like make sure that you have a good signal to noise ratio in the data. In those bands that will eliminate in W3 and W4, that will eliminate a lot of data. But if we work in W1 and W2, we keep a lot of the stars. But on the other hand, that means we can only look for like excess that it's strong enough in some sense, or at least leaks in the mid infrared. So that would be the two difference compared to other work. And specifically with regard to Suazo's work, they, on top of that, they don't just look for any kind of excess, right? They fit again Dyson sphere model. So there is this kind of like idea that Dyson spheres will create a specific type of morphologies in the excess or in this SED, and that's what they look for when we're like more. Let's look for like anything that's off, and so some of those might match. That's why I'm saying some of those might match Dyson sphere model, but other might not be because they're like too hot or something like that.
Just starting basically because you're looking for something, a speculative technology that someone may or may not do. We don't know. But with the Dyson Sphere, in a way, we are, because every time we launch a solar orbit spacecraft and abandon it, it's becoming part of a human Dyson swarm. So you do build that, and eventually that begins to emit in infrared. Over however many millions of years you need to be launching spacecraft into solar orbit, but eventually you have an infrared excess. And that's what this looks like. Now, how strong were these? And there were tens of candidates, as I recall, but how strong were they in infrared? I mean, was it just really, really obvious, or was it, somewhat subtle and you had to tease it out of the data?
Well, we keep the strongest one. I mean, we keep the obvious one, right? And we try to keep also the one that are in some ways reweighted to make sure that stars that would be very similar to the one that we're looking at don't have any error when they're predicted. So In a way, they are quite strong. I wouldn't be able to say like in terms of like infrared access. So like it's probably not able to detect like 3 satellites orbiting a star. So they're quite strong, and they match basically the type of access that's been either coined extreme debris disk or associated to planetary collision. So if you look at what we call fractional luminosity, it's like in the infrared, it's like 0.02 or something, like 2% of the fractional luminosity in the infrared. I wouldn't be able to completely give you like numbers in terms of like what does that mean in terms of like quantity of material around the star. There are some papers that do that. That's quite interesting. So we're looking into it right now. More in the planetary collision, not in the Dyson sphere regime.
That's interesting in and of itself, the planetary collision, because I would like to know just how common that is. And there have been at least one instance to my memory where we appeared to see an infrared flash from a system that appeared to be, a young system anyway, but it appeared to be a collision. And I think that was in the IRAS data that appeared that we just so happened to catch a protoplanetary collision within a debris disk. And that just seems to me to be interesting, because if it happens enough to where you can accidentally spot it the very first moment you can, then these things may be very common. And I wonder how common they are in mature star systems. We don't have that here, but at the same time, maybe other star systems are a lot less stable. So that would seem to be a fruitful area of research, right?
Yeah. Well, there is a recent paper, at least that come to mind. It's from Ken Worsey. I think it's a Nature paper. And basically, they detected it as an obscuration in the optical that happened after a rise in the infrared. And so they're not sure. I mean, I don't think they're saying they caught the events live, because it could also be like just that like you could imagine that there was like some kind of planetary collision, and then it comes and it orbits the star. But at least, and at the very least, they saw like a rise in the infrared. So basically, the star becomes an infrared access candidate. And then, like 2 years later, they saw this dip in the optical. And so their explanation is that maybe that there was a planetary collision, so that produced this excess in the infrared, and then that dust cloud came in the light of sight and produced this dip in the optical. I mean, although this would be, they're not like, from the top of my head, I don't remember if they're like super sure that's like the two events are linked, but that's also like, what are the odds? And I think this system is like 300 million years, which I don't know if that makes it old or young. I mean, it's still like not old. I don't know if it explains like instability or whatever. But I think also the nice thing about this work. I mean, one thing that we should try to do in our work is to figure out if we can make at least zeroth order conclusion on like the occurrence rate of these events. But it's quite hard to make like to give like strong conclusion on the occurrence rate. But yeah, after seeing this paper, and there are several of those like planetary collision candidates, sort of, I think like looking deeper in the time series in the infrared might be interesting.
Should be, because that collisional material is going to glow. It's going to absorb and re-emit infrared. Now, one interesting candidate here that was very different than what we're talking about was Tabby Star KSE 8462852, found in the Kepler data. Now, you work with the Kepler data with data mining and taking a second look back. What are you doing with the Kepler data now to see what did we miss?
So right now, I'm not doing anything with the Kepler data, but I think like, so related to this work, definitely using Kepler or specifically TESS, we have an interesting overlap with TESS. So the good thing is TESS could also like give information on the activity of the star in the optical, and so this can give information on the age, and so give some like hints if it's a young star or an old star. Although all of our stars are like on the main sequence, so they should be at least landed on the main sequence. They could just have arrived on the main sequence, but still. So this will be useful data. But on like side projects that I'm not necessarily like actively working on, but like trying to think about, like looking for weird signal. I mean, weird patterns in TESS or Kepler or this kind of time series would be quite fun. And we were like, playing around with ideas on like, if you could like modify artificially the way your own sun shines, what would be the obvious signal that you would want to send? It's probably not a signal that's periodic. It's probably not a signal that's symmetric. So you want to have like something that has a sharp decay and a slow rise, or something that is something that looks weird. And a lot of this, like a lot of Kepler data was used to find exoplanets, right? And if you're looking for exoplanet, you look for periodicity, which makes sense. But that means that, and looking for things that are not periodic makes things way harder, because the if it's periodic, then you see it more often, so you're more sure about the signal that you're observing. But if you're looking for things that are not periodic, it's a little bit more complicated. But I think that would be a fun project to just look for like weird pattern in Kepler or TESS or some of these things.
Now, how would you do that with machine learning? I mean, what you just said, how do you train an algorithm to look at a data set for unusual things? How do you do that? Weird things.
Yeah, that's a big question. Yeah, because we played with this idea, so we were going back and forth with like, how do we want to have a template, and then we can train the machine learning model to like find a specific template, like a type of pattern. But then that means you can only find this kind of pattern, which is a little bit like of a shame. But it's a good zeroth order, because that's the easiest way to do it. It's like then you have like a supervision. You can say, I want to have an algorithm that finds this template pattern, and so that's quite convenient. If you want to look for anything where like anything that's weird goes, especially in time series, it's very hard, because also one of there's a lot of like things that happen when you observe, when they gather the data. So most of the things that you will find are like just like bogus stuff, which is a little bit inconvenient. And so it really depends how you frame anomalies. So in the infrared access paper, it's makes life easier from machine learning perspective, because we frame anomalies as like conditional anomalies, like you're weird based on the other thing that we see about that star, like in the optical and stuff like that. But if you say what is an anomaly in general, you might want to think about it as some object that lies in a low density region of the data. And that's a little bit inside baseball, but basically doing density estimate on data that are high dimensional or very complicated, like time series, is super hard and highly non-trivial. And so it's also a big question for Vera Rubin, because one of the mission of Vera Rubin is to like discover new exotic transient, right? But that's they will gather a lot of data. So how do we make sure that we find those guys? And that's hard. So many people are thinking about these things, trying basically to encode what you observe in a space where you can kind of like that is more manageable than just like this big time series, is one of the main like high level idea. But again, it's not obvious how to do it well, and how to then interpret why the thing that you think is, the algorithm will tell you how this is weird, and then you're like, why? And then you have to figure out why. So that's also hard. I don't know if that answers your question, but it's a long line of research, so and very active.
And potentially very fruitful, because this, we look for certain things, and when you look outside the box, that's where the really interesting things are. And that was one thing with Kepler and KSE 8462852, is that they weren't looking for that, and it slipped through the cracks. But some amateurs on a citizen science project noticed it, simply because it was weird. And it just seems to me to be, that's where you find the good stuff, is when you're looking outside the box. Now, these candidates, and as I recall, there are 53 of them, potential Dyson Sphere candidates, but even if they're not, they're still interesting because they're unusual stars. Out of these 53 candidates, this was out of a huge sampling, right? So in other words, 53 sounds like a lot until you look at that you looked at 5 million stars, right?
Yeah, we technically did the search in 5 million stars, and we get 53 candidates, which gives you like a zeroth order occurrence rate of this event. And we're kind of sort of conservative in some of the cuts, but also you will always have additional, you can always double check for things, and that's more or less like like how astronomy work, I guess. So for instance, in the paper, like the version that's on archive doesn't have this, but like recently Jason Wright wrote to me to tell me like you should really do the radio check. And so I did that recently, and so some of our candidates, I think 6 of our candidates have a radio source nearby, so that might explain, if we have like some kind of like dust obscured galaxy aligned in the line of sight of the star, that might eliminate some of the candidates, maybe other things, but still, I mean, 50 is at the same time a big number and a small number because we search in 5 million stars. So it's a, yeah, so it's a fun number, I'd say.
It really is. 5 million is a lot. It's a lot to sort through.
But I mean, Gaia and Wise like observed a lot of stuff. Like 5 million is only because we work on the FGK main sequence. So we could just rerun the pipeline and work on the M dwarf because like it seems like Suazo's most of his their candidate in M dwarf. We could run it on A star. I mean, we could rerun the thing, and it's another bunch of millions, I guess.
Now, do you have plans to do that? Expand the search to Type M?
That would be cool. I do have plans. I don't know if I have the bandwidth and the time to do it, but I think if anyway, I mean the pipeline hopefully is well described in the paper. So I mean, if someone wants to run it, I think it would be interesting. Or we'll see. Maybe we can discuss with people. But yeah, that would be nice.
Now, what is
Also to
the
get that picture of how these things, if the rate change as the stereotype, that might also tell you something.
That's what I was getting at, is that can you, I mean, so another researcher comes along, they read your paper, and they're like, I want to look and see if these cluster. In other words, do these things, I mean, did you notice any patterns in these that gave you pause? Like, these are all clustered in one area of the Milky Way, within reason, of course. Or was it just random? In other words, they were coming from all different areas of the galaxy.
Uh, no, they didn't look like they were clustered. Also, I mean, we make some cuts, so we don't look in the galactic, like the like bulk part of the disk. We like look in less crowded area of the Milky Way to prevent like dust contamination and also like crowding and stuff like that. They don't look specifically crowded in any aspects. I had more like the problem is that although we look in 5 million and we get 53 candidates, and for some 53 is a big number, but for statistic 53 is not a lot. And so we make some plots like looking at color distribution, this kind of thing, or like absolute magnitude, and we see some like looks like there is, we don't have stars with like BP minus RP of 1, like why, but you don't know if it's random luck. I mean, we have 53 candidates, and some of them are going to get discarded even further down the line. So it's hard to like make any conclusion in terms of like talking about patterns when you have 50-ish points. You know what I mean? But in terms of like Milky Way distribution, no, they look like just like randomly distributed.
Is it possible to look at other data sets on the same stars and learn more? In other words, can you run a different sort of algorithm tailored for a different data set and try and see what these stars looked like in those observations? In other words, can you do cross observation science here by applying this, variations of how you've set up your machine learning to look and try to glean more information on these candidates?
Well, first to clarify, this is already like cross-matching. I mean, merging several data sets together. It's using Gaia, TUMAS, and WISE together. Yeah, I have to investigate what other data set we can like add on top of that to like get more information on those stars. But it might all be either wavelengths that we already have, but like a different way of so like test, like we get in the optical, but we would get like time series in like like 3 months length time series. So that's still cool. Yeah, I'm not sure I completely got what you meant with the like rerunning the algorithm, like finding different type of anomalies or just checking if there are anomalies in other aspects.
Well, just to even just check. In other words, all right, we see this infrared excess in this data set. Do we see the same infrared excess in another one?
Yes,
Is
yeah.
basically what I'm saying. Is that can you confirm you're reading from one instrument's data set versus another with this method?
Yeah, I have to double check which overlap because I mean, WISE is like one of the it's it's really big. So usually it's the one that will cover the most. So it's not necessarily, and also like the resolution is better. So it's hard then if we go to a different data set like or an older data set, and like the source were not resolved properly. Like if you have like say three stars, that appears like close to each other, they are resolved by WISE, and WISE can tell you, oh, this star is this bright, this star is this bright, and this star is this bright. But other mission, if they're slightly older or whatever, they might not have that resolution, and so they won't give you like a quite accurate number. But yeah, I mean, this is definitely something that we should investigate as well. But maybe I'm greedy. I would like to have follow-up observation as well. So more data, say from JWST, that would be cool. But
Yeah, so say we gave you unlimited time on the James Webb Space Telescope. Do you have any favorite candidates that came out of this study? In other words, ones that you're like, that's really weird, even for what I'm looking for, which is already strange. Where would you point the telescope?
that's a good question. I mean, I don't even need unlimited time. I think will be reasonable. But if we do the proposal, actually, I might be in favor of like I mean, at least in the as far as I interpret it, when we from this set of candidate, we see some kind of like a distribution. Like we have some strong infrared access and like different shapes. If we just look at the plots, basically, so I would be in favor of like trying to like sample like these different shapes so we could maybe get a better understanding if some of those are like if it's like a continuum, maybe saying, oh, those are like different planetary mass collision or this kind of thing. And if we start getting to the extreme one, then maybe it's going to be like challenging to explain or lead to interesting stuff. But if you have this kind of continuum that can give you an idea of like when things start getting weird in those weirdos, right? I don't know if that makes sense, but
Everything in astrophysics starts as a weird event, something you don't understand that you've never seen before. So if you think back, the discovery of pulsars was, oh, that's weird, and didn't really understand what that was until, we figured it out. And anything else, quasars, it all happened that way. So the weird stuff is where the good stuff is because in astrophysics, because that's where the new discoveries are. And that's what excites me about data mining like this, is that you can spot things that were missed because the people that were looking for something weren't looking for this. Right now, Gabriella, it seems to me to be a fruitful area to look at within astrophysics, obviously, is to look at these old data sets again. And that is where discoveries are made, because if you're not looking for something, you'll miss things. But when you look at the history of astronomy, that's where the really interesting stuff lies. In other words, that's how we discovered things like quasars and pulsars, Joshua Bell Burnell, that we weren't looking for it, but just happened to notice it. Just happened to notice something was off, and there it was. In this day and age of automatically taking data sets and sifting, we might be missing those types of things. And I think that that's probably the most interesting area here is things missed. Now, could you write, and this expands on an earlier question, could you write a sort of data sifting algorithm specifically to look for extreme outliers? In other words, things that just make no sense whatsoever. I mean, can you do that, or what constraints do you have on what you can look for when mining a data set?
that's a good question. Well, I can write it. Doesn't mean it would be right, but or correct. But this, I mean, this opens a lot of questions in terms of like, what is the nature of the data that you're looking at? Are those, like the similar data that we've been working on in this infrared search, like tabular, or what I would call tabular data, meaning that you have like specific column, and you know it's like, oh, the magnitude in this band, the magnitude in that band, the parallax, blah blah blah. You can, so it depends on the nature of the data, or it can be, if it's images, it's going to be different. If it's time series, it's going to be different, harder. If it's spectra, it's going to be higher dimensional, of course. So in principle, I mean, you also need basically the more things you look at for a star, so the more dimension you see about an object, I mean, or in general, uh, if you're looking for, that means you have a higher dimensional space, and so you need more data to understand what is weird. And just looking for things that are weird in some ways is doable, because you can just say, this is weird because you have no neighbors, you have no one that is similar to you. But this kind of approach can break, say, because of in high dimension, when you look at many different aspects of a star, say like if you have lots of high dimension, I don't know if that makes sense but to your auditor, but that might break. So, and on the other hand, that one of the issue is that, what if this is weird because we don't understand it? I mean, not because it's weird, but because we don't have a model for it. But this weird thing still has, 50 friends. Then your algorithm won't find it, because it's not completely alone. It has 50 other weirdos with it. And so this is the kind of thing I try to think in my research, is that what is an anomaly in this context, and how do you build this kind of algorithm to find anomalies, and depending on how you define them. I went on a very long-winded answer. Sorry.
I like long-winded answers. It means I don't have to speak. Now, what do you, as a data scientist, what do you think, Doctor, the future in much broader terms looks like for being able to do these sorts of things and look at data sets? In other words, do you see advances in medical science coming from this as we look at, protein folding or something like that, in data sets past taken, using similar sorts of methods to look for weird outliers that may be very important?
You were cutting a little bit, but I think I got the bulk of your question. Yeah, I mean, I would be super curious to also learn more about medical application, biology application, and I think that, yeah, getting a better, because, okay, on one hand, we have this, like, the revolution of deep learning, and a lot of people are cashing on the hype, and it's also like a very powerful tool. And one of the potentially interesting aspect of these tools is the ability of like aggregating a large quantity of data that lies in like this high dimensional space, very complicated, that we cannot look at, and put it in a smaller, like, summarized way. And so then you can work in that space. And that's called, representation learning, dimensionality reduction, all of these things in data mining and deep learning, machine learning methods. And that can be very, very useful and interesting, because that gives you a way to like basically open your data in a more, in a way that you can plot, because we're very limited as human. We like two-dimensional things, maybe three. So that's cool. But on the other hand, the thing that's not so cool is that we still don't necessarily understand what properties of the data they will keep. Will they keep some cluster? Like, if your data were clustering in some ways in your high dimensional space, will it keep the cluster in the low dimensional space? If you have an outlier in the high dimensional space, will you still see that outlier in the low dimensional space? And by trying to have something that tries to do everything at the same time, you might end up losing, of course, some of the specificities of your method or of your data. So, yeah, one of my research interests is to try to understand this issues and the limitation and the properties of this algorithm. And of course, I mean, this is also of interest in the field of bio, because they have all of this, like huge RNA sequencing things, the protein folding, all of this, the drug discovery aspect are also like, all of these data, they lie in a high dimension. And if you could just understand how they're distributed and how they work together in this high dimension, that would help a lot. But it's hard.
Do you see a future in, with our advancing AI, insofar as it's advancing and doing it in weird ways apparently, but with advancing artificial intelligence, do you see an expansion in your ability to look at these data sets? In other words, does a smarter algorithm help you, or do you think that, well, this is about as far as we're going to get with this technique right now?
That's a deep question. I don't think I can make like a hard prediction or opinion. I think it's definitely worthwhile to investigate this kind of method. I'm not an expert on all of them, obviously. I I don't know, maybe it's my simple mind. I want to understand first the simple method and then we'll go deeper. But of course there is huge interest in designing this method further, right? I mean, this is my background is actually computer science and machine learning. So I went through astrophysics after doing my PhD in machine learning. So I can't say, like, stop doing machine learning and deep learning. That would be very weird, just because of how I was, trained. But yeah, I think just like having a good understanding of what you get from this method, at least from the dimensionality reduction perspective, is is really important. I kind of skeptical about, like super large model that will do everything for you and just give you something out. But also, but what do I know?
So where do we go from here? So we have these candidates, these 53 candidates from your study, and then 7 from the other paper. We have these candidates. So enterprising researcher comes along, reads the paper, and says, well, let's look into these. What's the next step? In other words, looking at these candidates, so where do we go from here as far as determining if they, what their origin is? I don't want to go too far and say whether or not they're a Dyson sphere or whatever, because that gets kind of ambiguous eventually, but unless you nail it. But what's the next step for this research?
Well, hopefully we'll write a JWST proposal. I don't want to, sell the thing before it's actually written, but that would be nice. I have to look into what other facilities we could use for follow-up observation that would make sense in this context. Because maybe ground-based could also work, but I'm not familiar enough with like different type of facilities. So I think we should discuss, and probably I will chat with Jason Wright as well on that regard. If we want to have like a joint effort, for instance, depending on the type of proposal we want to write. So yeah, I think getting spectra in the infrared would be quite useful, at least to like better characterize the morphology of the excess and see if we see emission line, absorption line, and so on and so forth. That would be quite informative. And so that would be the next step for sure. But I think we would reduce the set of candidates to look at, obviously.
All right, Dr. Contardo, thank you for joining us today, and I look forward to more papers and more research into this. This is really intriguing because, if you find something that you can't really immediately explain, and then after a bunch of observation, you still can't explain it, interesting territory indeed. Thank you for joining us today.
Thank you for having me.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.